I was in a small tech gathering in Austin a few weeks ago, and I ended up sitting across from a senior policy advisor who's spent his career drafting safety regulations for emerging tech. He was remarkably calm, almost smug, as he explained how his department planned to throttle the next generation of AI chips to ensure public safety. He spoke about technology as if it were an unruly dog that just needed a shorter leash, convinced that a few well-placed guardrails can keep the future under his control. But then the conversation turned to the new AI factories rising in the desert, those massive gigawatt-scale engines designed to literally manufacture intelligence. His demeanor shifted instantly. He didn't offer any counter-arguments about energy efficiency or economic theory. Instead, he started scrolling through his phone, showing me headlines about the latest Starship flight. "They aren't even asking for permission anymore," he whispered, his voice tightening with a kind of suppressed panic. "They're just building it." To him, the fact that we were moving heavy industry into orbit wasn't a triumph. It was a direct insult to the bureaucracy he represented. What was truly bizarre, though, was his reaction to the latest breakthroughs in neural interfaces. He didn't see a cure for paralysis or a gateway to new cognition. He saw a biological security risk that needed to be banned. He actually used the phrase moral hazard to describe people choosing to optimize their own brains. The more he talked, the more I realized his entire worldview was built on the idea that human progress is a defect that needs to be managed, rather than a force to be unleashed. That sudden transition from professional confidence to a kind of desperate defensive anger was revealing. It made me realize that the battle for 2026 isn't just about chips or rockets or neurons. It's a fundamental clash between those who want to manage our decline and those who are ready to ignite the engine. Left me wondering, if we continue to treat every leap forward as a crime, will we even be the ones who get to see what's on the other side?
That anecdote, it perfectly captures the core tension right now and what we're seeing across the entire technological landscape.
It really does.
It's this deep-seated anxiety surrounding rapid, simultaneous progress across multiple fundamental domains. Progress that simply cannot be contained or, controlled using the regulatory models that were built for the 20th century.
Right. They're trying to apply old rules to a completely new game.
Exactly. We are seeing builders literally ignite the engine on 3 foundational vectors, and the speed and scale of that ignition is what generates the panic you witnessed.
It's the ultimate feeling of being overwhelmed by the pace of change, and that's why this deep dive is so crucial. We're going to break down these 3 specific acceleration vectors. The infrastructure needed to create intelligence, the physical industrialization of space, and then the actual technological redefinition of human biology. It's about synthesizing how these forces are converging to create an entirely new epoch, something that's often just labeled as acceleration.
And it really boils down to 3 categories of foundational shifts. First, you have the infrastructure for intelligence, and we're specifically talking at the gigawatt scale.
Yeah, the physical scale is key.
Second, the industrialization of physical scale, with access to orbit becoming an economic platform. And third, the redefinition of human biological limits through things like neurotechnology and cellular reprogramming.
So let's start right where my story began. The sheer scale of the new digital engines that are driving civilization.
Let's do it.
When we talk about the AI arms race, I think we have to stop imagining, abstract software models. We are talking about building industrial scale, physical, multi-acre data centers, AI factories. That's the term they're using. And it's accurate. They're designed to literally manufacture intelligence.
Right. And the scale of sovereign compute being pursued globally right now is staggering, especially here in the US.
We've moved beyond incremental increases, haven't we?
Oh, completely. We are squarely in the era of sovereign compute, where national security and economic dominance are measured in exaflops. We're seeing NVIDIA in this direct, deep collaboration with the U.S. Department of Energy.
And not just them, but partnering with premier national laboratories like Argonne and Los Alamos National Laboratory, LANL.
Exactly. And these are not just academic partnerships. They are actively constructing massive, bespoke AI supercomputers.
And the numbers involved, they truly defy comprehension for anyone who's used to standard enterprise computing. Can we just walk through the scale of what we're talking about here?
We can. Let's take the Solstice system. It's a key project in collaboration with Oracle and the DOE. That system alone is planned to feature 100,000 of NVIDIA's new Blackwell GPUs.
100,000.
100,000. Now, when that system is paired with its smaller counterpart, the Equinox system, which has another 10,000 Blackwell GPUs, you were looking at a combined capability of 2,200 exaflops of AI performance.
2,200 exaflops. I have to stop there for a second. To put that into perspective for you, an exaflop is 1 quintillion calculations per second. That's a 1 followed by 18 zeros. The very first machine to break the single exaflop barrier only did so in 2022.
Yeah, just a couple of years ago.
And now we are talking about building systems that have over 2,000 times that capability, and they're dedicated specifically to AI workloads.
That's it. These massive systems are specifically designed to drive technological leadership across U.S. security, science, and energy applications. The mission is it's unambiguous, maintaining global technological supremacy.
And that includes the really sensitive, the classified work. Los Alamos, LANL, they're integrating this advanced infrastructure through the Vera Rubin platform. But they also have the classified mission system, ATS-5, which is expected to be operational by late 2027.
Right. And this isn't just about modeling climate change or, protein folding. This is foundational compute for national security and strategic defense applications. The stakes just couldn't be higher.
They really can't. But this kind of rapid scaling immediately brings us to the elephant in the room: energy.
The power. Always the power.
This shift isn't just about speed. It's about the fundamental, exponentially increasing energy required to power these machines. This power crisis is now the single largest constraint and, kind of paradoxically, the biggest driver of innovation.
It really is. I mean, I remember when we were shocked by a high-end graphics card pulling, a mere 200 watts?
Yeah, that was the benchmark for years. That was a power-hungry card.
That was the consumer baseline. Now, just look at the trajectory defining the enterprise sector. The current workhorse, the NVIDIA H100, is already pulling 350 watts.
Okay, that's already a big jump.
But the upcoming generation pushes that dramatically. The Blackwell B200 is expected to consume up to 1,200 watts. And the ultimate configuration, the integrated Grace Blackwell GB200, is a whopping 2,700 watts per package.
I have to pause there. You're telling me a single compute package, one chip, is now requiring nearly 3 kilowatts of power.
3 kilowatts, yeah.
That reframes the entire definition of power consumer. That kind of exponential increase means traditional data center power consumption, which we used to measure in megawatts, is now scaling to gigawatts.
Precisely. A single data center campus drawing a gigawatt of power. And the traditional power grid infrastructure, it simply cannot keep pace with that kind of demand profile. It's not built for it.
So what's the solution?
This is why we're seeing this remarkable strategic convergence. The major AI data center companies, Amazon, Microsoft, Google, they're not just negotiating for better energy rates anymore, which they've done for years.
Oh, that's old news.
They are striking deals with power companies to build their own new dedicated generation capacity. They're often targeting small modular reactors, SMRs, to meet this gigawatt-scale demand.
So they've done the math. They've calculated that the only way to ensure the foundational infrastructure for sovereign compute and really energy superabundance in this AI arms race is to bypass the traditional power grid limitations entirely.
They're becoming, in effect, their own independent utilities.
It's a profound shift in corporate strategy, isn't it? Tying the infrastructure for intelligence directly to the infrastructure for energy superabundance.
It is. And this intense pressure, it forces radical innovation in design, which is why NVIDIA is developing what they call the AI Factory Blueprint.
Tell us about that blueprint. Where are they building this, and how does this whole digital twin concept work in practice?
So the centerpiece is the NVIDIA AI Factory Research Center in Virginia, and it's powered by the Vera Rubin platform. This center is not just another data center, it's a living laboratory, a testing ground.
A proof of concept.
Exactly. It serves as the groundwork for the NVIDIA Omniverse Deus Ex, which is the actual replicable blueprint for these multi-generation gigawatt-scale build-outs.
So they are building a perfect, constantly updated virtual version of the physical factory. A digital twin. What is the twin actually optimizing for?
Everything. Absolutely everything. The digital twin integrates the virtual and physical systems, allowing them to simulate and continuously optimize the factory for 3 core metrics: raw performance, energy efficiency, and sustainability.
So they can test things out in the virtual world before committing in the real one.
Precisely. They can test thousands of operating scenarios, different cooling protocols, varying power loads, component wear and tear all virtually before implementing a change physically. This significantly reduces downtime and, more importantly, energy waste.
And to manage something this complex, they're bringing in the heavy hitters from traditional infrastructure, right? It's not just a software problem.
Absolutely not. The optimization partners are a critical part of the blueprint. This is an engineering and civil construction challenge at its core. You've got engineering giants like Bechtel and Jacobs,
Okay, the big names.
alongside power and cooling specialists like Tesla, Trane, Hitachi, and Siemens Energy. This partnership is essential because optimizing a gigawatt facility involves coordinating physical systems, massive cooling loops, high voltage power distribution, all in real time.
The ultimate closed-loop system must require some kind of autonomous management, though. I mean, the sheer volume of data, the power flow, the cooling dynamics, humans can't possibly manage it fast enough to maintain peak efficiency.
No, you're right, they can't. And that's the next layer of complexity. The system relies on advanced AI agents from companies like Emerald AI and Phaedra.
So AI is managing the AI factory.
Essentially, yes. These agents continuously optimize power, cooling, and workloads. They don't just react to problems, they dynamically interact with the utility networks, acting as a massive intelligent load.
What does that mean for the grid?
It means this proactive management significantly boosts grid flexibility and resilience, which is crucial when a single facility is capable of destabilizing the local grid by drawing gigawatts of power on demand. It can predict its own needs and coordinate with the utility.
That level of demand management must force extreme efficiency at the chip level as well. I mean, if you're building a gigawatt factory, a tiny 1% efficiency gain translates to millions of dollars in megawatts saved.
It does, and that brings us to one of the most surprising and technically fascinating nuggets from the data, the hidden efficiency battle that's focused on performance per watt, or PPW.
PPW. So that's the metric that's replaced raw speed.
It absolutely has. It's the rate of computation delivered per watt consumed. And here's the counterintuitive part. Conventionally, programmers always try to maximize resource utilization. Getting higher occupancy in a GPU kernel always meant better performance.
Right, fill up the chip.
But the research shows that when you factor in power consumption, that intuition is often completely wrong.
Okay, let's dive into the technical nuance here, because this seems to explain how they can cut power without cutting performance significantly. It centers on something called the vector register files, or VReg files. What are they and why are they drawing so much dormant power?
So in simple terms, a GPU is designed for massive parallelism. To support the thousands of parallel threads it runs simultaneously, it's built with these massive high-speed memory structures called vector register files, VReg files. These are essential SRAM structures, incredibly fast, but they have a physical limitation. They consume power. They consume both static power, just from being turned on, and dynamic power when writing or reading data. And they do this even when they are not actively being used by the running program.
So if I write a piece of code that only needs a few registers, but the physical architecture reserves a huge block of memory for my code, I'm paying the power bill for that reserved dormant memory.
That is it, exactly. The data show that in a large majority of common GPU applications, the registers are drastically underutilized. We're talking about 6 out of 10 applications having more than 50% wasted register capacity. Sometimes it's closer to 70%.
Wow.
So even if you maximize the number of threads running, you get that high occupancy you're always told to aim for. If those threads aren't utilizing the full register capacity, you are drawing significant static power for that dormant space.
That sounds like a fundamental architectural inefficiency baked into traditional GPU design.
It is. And the key finding for power optimization is this. By tuning the VReg file lane size, basically, matching the physical allocation of memory to the actual kernel's requirements, rather than relying on a one-size-fits-all maximum, you maximize PPW.
So you give the program exactly what it needs and no more.
Exactly. The baseline architecture they studied uses 256 VGPRs. Research demonstrated that by shrinking this allocation to an optimal size, say 160 VGPRs, the performance degradation was statistically minimal, only about 1.2% on average. But the power savings achieved were significant, around 7.13%.
7% power savings on these massive AI clusters for a 1% performance hit. That is a massive return on investment, and it shows the engineering mentality has fundamentally shifted from maximizing raw FLOPs to maximizing efficiency per unit of energy.
The math speaks for itself. For critical AI workloads like matrix multiplication, the peak PPW was actually achieved with only 152 physical VGPRs, which is far below that hardwired baseline. This kind of optimization ensures that every single watt delivered by that gigawatt-scale AI factory is delivering maximum computational value. It's what makes the whole system economically viable and strategically superior.
Okay, so we've established the gigawatt-scale infrastructure needed to generate intelligence on Earth. Now, let's shift our focus completely. Let's go from the digital to the physical, to the industrialization platform that enables humanity to operate beyond Earth, the Starship system. This is the ultimate example of the just build it mentality applied to heavy industry. It represents a paradigm shift from digital scale to physical orbital mass throughput.
And this is exactly where the policy advisor in your opening story really started to panic. Starship is not an incremental improvement on a rocket. It is an economic weapon designed to render current launch vehicles obsolete.
It's a category killer.
It is. And even the most pessimistic technical assessments of the vehicle, like the detailed analysis from the German Aerospace Center, the DLR that we examined, even they agree on one fundamental point. The system is highly disruptive. It will shift the launch market paradigm, even if its initial flight rates are slow.
They can't deny the basic physics and economics of it.
No, they conceded that the company has already demonstrated its ability to continuously disrupt the technical and economic status quo.
And that disruption is rooted in quantifiable mass. What is the true capability we are discussing here? I think people have a hard time grasping the numbers.
Let's try to ground it. When it's fully reusable, Starship's estimated payload capacity to low Earth orbit, or LEO, sits reliably in the 90 to 100-ton range.
90 to 100 tons.
Right. And if they operate it expendably, which they generally won't, but the capability exists, that number jumps to around 200 tons.
Okay, let's make that scale real for everyone listening. To put that 96-ton capacity into perspective, the entirety of China's current 96-ton Tiangong space station, which was built over years and required multiple expensive launches, could potentially be launched in one go by Starship. That capability fundamentally transforms space construction from a logistical nightmare into a simple heavy lift operation.
And the economic disruption is, frankly, the true headline here. Just think about what we currently consider big space construction. Skylab, the original U.S. space station, had about 350 cubic meters of pressurized volume. It cost about $17 billion in current dollars for 2 flight units.
And the gold standard, the International Space Station, required something like 25 complex space shuttle launches just to deploy its major components. The total project cost is staggering over $150 billion across all partners over 3 decades.
Now, contrast that staggering figure with the Starship estimate. A single Starship upper stage can be configured as an enlarged Skylab module. It would have about 1,100 cubic meters of pressurized volume.
So substantially larger than the ISS.
Substantially larger than the ISS's 913 cubic meters. And the deployment cost could be around $5 billion.
Wait, let's be absolutely clear on this. A single launch vehicle is capable of deploying a space station module larger than the entire ISS, and the cost difference is between $150 billion and a possible $5 billion.
That's the analysis.
That's not a revolution. That is an economic collapse of the previous paradigm. It turns government procurement into industrial procurement.
It absolutely shifts the entire mental paradigm surrounding orbital construction. Suddenly, accessing massive volumes and masses in orbit isn't this multinational, multi-decade struggle constrained by extreme budgeting. It just becomes an industrial logistics problem.
It also requires a philosophical shift in how we even discuss launch capability. I know one of our sources noted this. It bugs analysts when people say reusability reduces payload. The shift is that non-reusability increases payload only because you're throwing away the most expensive part of the vehicle.
Exactly. Reusability is now the baseline expectation for any viable future system. Anything else is just an expensive concession.
And that philosophy is backed by their operational approach. This kind of rapid, cost-effective scaling is only possible because they successfully applied modern software development methodologies. That iterative, fail often, fail early approach to complex billion-dollar space hardware.
Right. That continuous public learning cycle demonstrates a level of confidence and expertise that traditional risk-averse aerospace models simply can't match. And it results in these rapid development cycles that regulators are, frankly, struggling to even track.
That continuous acceleration is the builder's mindset. Confidence backed by continuous public failure and learning. But for this to be a true industrial platform, they have to solve the logistical complexity of high flight cadence, which necessarily includes orbital refueling.
And that is the single largest technical hurdle for deep space missions. Starship's massive scale means it requires propellant transfer in low Earth orbit to reach destinations like the Moon or Mars.
So it's not a single launch and go.
No. This is an entirely new operational task that involves multiple Starship launches. Perhaps 8 to 10 of them, just to ferry propellant up to a tanker that's awaiting the main spacecraft. It's a complex, choreographed logistics chain that requires continuous, high-reliability launch cadence.
So Starship isn't just a rocket. It's the anchor of a completely new, integrated logistics network in orbit.
Precisely. And this exponential mass throughput immediately forces competitors to adapt. China's reusable rockets, for example, are incorporating key Starship concepts. You see them using stainless steel construction, methalox fuel.
So they're copying the homework.
They are, but as has been noted, these competitors are essentially applying these concepts to a Falcon 9-style architecture, which, while it's competitive with the Falcon 9, means they're still in another league compared to Starship's full, refuelable deep space capability.
So Starship is forcing global innovation, but it remains the vanguard, setting the industrial pace. What about the long-term vision of colonization? Is Starship the final answer, or is it a stepping stone?
That's where the vision gets truly strategic. Even some proponents suggest Starship might be a bridge or an industrial ferry rather than the final interplanetary hauler.
What do you mean by that?
Well, while it is a brilliant launch vehicle optimized for escaping Earth's massive gravity well and then landing safely, true Martian colonization might eventually require true spacecraft. We're talking massive ships assembled on orbit, potentially using extremely efficient, high-ISP nuclear propulsion systems.
High ISP meaning high specific impulse, getting the most thrust out of the least amount of fuel.
Exactly. The propulsion is dramatically more efficient, but those systems aren't designed to survive the high G-forces of escaping Earth's atmosphere.
Right.
So Starship, in this context, becomes the indispensable delivery truck. It transports the raw materials, the propellant, the initial cruise up to VO, but the actual heavy lift for interplanetary travel might favor infrastructure like orbital skyhooks or tethers that essentially front-load the energy costs, making propellant use extremely efficient for the final transit.
So Starship is the necessary industrial starting point. Its whole architecture is fundamentally compromised by the need to be aerodynamic and capable of high-G atmospheric operations. You need Starship first to deliver the thousands of tons of material to LEO to build those subsequent, more specialized systems.
You've got it. So we've covered the digital scale of intelligence and the physical industrial scale in space. Now we have to pivot to the third vector, the human biological scale.
Yeah.
If AI is the new brain of civilization and Starship is its skeleton, we are now looking at the enhancement frontier, the technology that's trying to make our own minds and bodies faster, stronger, and longer lasting.
And this is the acceleration vector that generates the greatest defensive reaction, just like that policy advisor I mentioned. The technology here is literally crossing the threshold of what it means to be fundamentally human. Let's start with neurotechnology. The interface to thought itself, brain-computer interfaces, or BCIs.
The definition is simple, yet profound. These are devices enabling the exchange of messages solely through thought, completely bypassing physical movement. It's the ability to communicate or control a machine using only your neural signals.
The history feels like something out of science fiction, but the inception dates back surprisingly far, all the way to 1964.
That was the foundational moment established by Dr. Gray Walter. He conducted an experiment where he attached electrodes to a patient's skull and observed a spike in brain activity, what we now call the readiness potential, milliseconds before the patient physically pushed a switch to control a projection device.
So the brain signal came first.
The signal came first, and that spike was enough to activate the device on its own. That signified the first instance of a device being manipulated completely absent of physical muscular motion. The thought was the action.
Now, in the modern era, the high bandwidth interface is rapidly becoming a reality, but it's happening through two very different approaches, really exemplified by the two leading pioneers, Neuralink and Synchron.
Right. Neuralink, with its very ambitious goals, is pursuing an invasive, high-bandwidth BCI. Their Link device uses these tiny, flexible polymer probes containing thousands of electrodes that are implanted directly into brain tissue.
And their vision is broad.
Very. It's a consumer-focused, accessible device designed to be medically relevant, treating paralysis or blindness, and also connecting via standard protocols like USB and wireless capabilities.
But the invasiveness is the major point of friction and regulatory concern, isn't it?
Oh, absolutely. Initially, Neuralink faced a significant rejection from the FDA for human trials. The primary concerns revolved around the migration of those tiny flexible wires to other areas of the brain, and the lack of a clearly defined safe procedure for removing the device without causing damage to surrounding brain tissue.
And they did eventually get approval.
They did. They later received conditional approval in 2023, but those initial hurdles really underscore the regulatory complexity of high-bandwidth invasive technology operating directly in the human brain.
And then you have Synchron, which took a much more cautious, minimally invasive path.
Right. Synchron pursued a neuroendovascular implant. Their sensor, which is called a stentrode, is delivered via a catheter through blood vessels, specifically the jugular vein, and deployed in the cerebral cortex.
So no open brain surgery.
Exactly. Because it avoids open brain surgery entirely, it significantly reduces trauma. And that minimal invasiveness granted them FDA approval for human trials much earlier than Neuralink, which really highlights the regulatory advantage of a less radical procedure.
The scope of BCIs is also moving rapidly beyond just medical applications, right? This isn't just about fixing things anymore.
No, it's not. While the initial focus is neurorehabilitation for conditions like ALS, stroke, and communication deficits, the scope is expanding into extraclinical purposes. We are seeing major investment in gaming, wellness monitoring, and ultimately pure cognitive enhancement, the optimization of the healthy brain.
And that expansion, moving from curing a deficit to enhancing a capability, is where the intense bioethical conflict really begins, starting with the risks to autonomy and privacy.
The autonomy risk is fundamental because invasive BCIs require a surgical integration with the self. Critics fear a loss of autonomy if the technology becomes too integrated into one's sense of self-image.
What does that loss of autonomy actually look like for a user? What does that feel like?
We have actual patient reports that detail changes in self-perception. Some individuals with BCI implants reported feeling powerless or experienced a reduced connection to their own identity, particularly if they already struggled with issues like low self-esteem.
Wow.
One 2017 study of 6 patients noted one subject explicitly stated the BCI made them feel powerless. So this raises the alarming possibility that technology designed to restore movement or communication could inadvertently infringe on the self-determination of the user.
And the privacy risk, or mental integrity, seems even more immediate in the age of data harvesting. The fear is unauthorized access to your thoughts and emotions.
Right. And while some ethicists argue that current mind-reading capabilities are technically constrained, they're often restricted to a constrained selection approach, where a user chooses from a fixed range of possibilities. BCI data is inherently sensitive in a way that goes far beyond simple medical records.
How so?
It can reveal critical, minute-by-minute insights into a person's wellness, their mental function, their internal monologue, and even their character attributes.
And the risk profile skyrockets when you connect a brain interface to the network.
This is the most novel ethical concern, specifically concerning technologies like Neuralink, which intend to operate constantly. The device is designed to communicate constantly via smartphones, third-party apps, cloud storage.
So it's always on.
Always on. And this raises massive cybercrime risks. We're talking about potential remote hacking, not just to steal data, but to conduct unauthorized neural activation or trigger negative reactions like sudden pain or panic. This constitutes an actual physical harm and a direct violation of the non-maleficence principle.
If a hacker can access your bank account, what happens when they can access your brain? This feels like it requires a proactive, forward-looking regulatory framework, which brings us to the concept of neuro rights.
The legal argument is compelling. Existing informational privacy laws, like the Fourth Amendment in the US, they may be insufficient for this. Neural data is considered far more representative of one's true identity and self-determination than, say, a DNA sample or a blood test. It requires explicit new protection.
And the Morningside Group proposed 5 key neuro rights to address this legal gap. Let's detail those, because they really form the foundational ethical framework for this technology.
Okay, the 5 rights. First, the right to personal identity, which ensures the user maintains control over their identity and sense of self. Second, the right to free will, protecting against involuntary control or manipulation. Third is the right to mental privacy, ensuring that neural data is never accessed or used without explicit, conscious consent. Fourth, the right to equal access to cognitive enhancement, which addresses concerns that these technologies could create a biological divide between the enhanced and the non-enhanced.
And the 5th right, what does that cover?
The 5th is the right to protection against algorithmic bias. Since BCIs are driven by complex AI interpreting neural signals, this right seeks to prevent the exclusion or misdiagnosis of specific groups due to, say, unrepresentative training data. It's about safeguarding fairness in who can benefit from the technology.
And beyond rights for the user, There's also the proposed technocratic oath for developers, which is inspired by the Hippocratic Oath for physicians.
Yeah, and this is an attempt to inject a framework of moral standards into the development process itself. It mandates principles like non-maleficence, do no harm, beneficence, strive to do good, justice, ensure fair and unbiased outcomes, and transparency, committing to make algorithms as clear and adaptable as possible.
So it's about making sure the tech serves humanity.
Right, that it serves humanity as an end, not merely a means to capital or research goals.
That focus on enhancement and overcoming biological limitations brings us to our final acceleration point in this section, age reversal. Here, we're moving from the mind interface down to the cellular level.
This is the science of cellular reprogramming, a technique that performs what's called partial epigenetic reprogramming. It's based on the discovery of specific genes known as Yamanaka factors OCT53, SOX2, and KLF4.
And how do they get those into the cells?
These genes are delivered into cells via gene therapy, typically using AAV-mediated delivery.
What exactly is AAV-mediated delivery and why are they using it?
So AAV stands for adeno-associated virus. It's a small, naturally occurring virus that has been modified in the lab to be harmless. Researchers use it as a delivery vehicle, or a vector, because it's highly efficient at entering various cell types and delivering the specific genetic material, in this case, the Yamanaka factors, into the cell's nucleus. It's essentially a highly targeted microscopic syringe.
And the mechanism is basically hacking DNA to revert the cell's age, but without turning it into a stem cell, which is the crucial distinction, right?
That is the critical distinction. The Yamanaka factors turn on genes that momentarily revert the cells to a younger epigenetic age, but the process has to be partial. It must reverse age without causing the cell to lose its original identity, its terminal differentiation.
Because what happens if it goes too far?
Well, if a neuron reverts all the way back to a fully undifferentiated stem cell, it ceases to function as a neuron and can form tumors. The breakthrough is finding the precise timing and combination of factors to shave years off the cell's epigenetic clock while maintaining its cellular purpose. Studies have already shown success in reversing human skin cells by 30 years.
And what about the in vivo results? What are we seeing in live animals?
The results are significant and they're constantly accelerating. Studies showed success in extending the lifespan of prematurely aged mice by 20%. More recently, researchers successfully extended the lifespan of naturally aged mice using only 3 factors OSK, which demonstrated increased safety.
That's incredible.
And perhaps the most compelling breakthroughs involve organ function. The technique has successfully restored vision in mice and non-human primates.
That leap from a lab dish to restoring a complex sensory function is staggering. And naturally, that kind of potential has attracted the massive capital that we saw defining the AI infrastructure sector.
The funding acceleration is immense. This is not fringe science anymore. You have Google's Calico, the Jeff Bezos-supported Altos Labs, and most recently, Sam Altman's $180 million investment in Retro Biosciences, which is dedicated explicitly to extending the human lifespan. All of this demonstrates a collective belief that true rejuvenation biotech is on the cusp of an explosion.
But the main challenge remains the initial safety concern that plagued the discovery of these factors in the first place, the cancer risk.
Absolutely. The original combination of all 4 Yamanaka factors caused massive tumor growth in early experiments, so the key remaining challenge is twofold: preventing the accidental induction of cancer and ensuring that the gene therapy targets only specific cell groups in the body to ensure precise control over the reprogramming process.
So delivery and safety.
Delivery and safety. If they can solve that mechanism, which many estimate is less than a decade away, human testing will move from being science fiction to a logistical inevitability.
So we've now synthesized the 3 foundational shifts: the gigawatt-scale infrastructure for intelligence, the industrial-scale platform for moving materials into orbit, and the fundamental re-engineering of the human brain and body.
And what makes this era so unique is that these forces are accelerating simultaneously.
This confluence of power compute, logistics, and biology, it requires some kind of philosophical framework to justify and interpret the speed. And that's where effective accelerationism, or ENIAC, enters the conversation.
Right. Each rocket is viewed by some in the tech world as a revival of earlier movements like extropianism and transhumanism. At its core, it's an ideology advocating for the total, unapologetic unleashing of technology and capital to maximize wealth and progress for the species. It aggressively rejects what it views as regulatory stagnation or safetyism.
It is the philosophy that rationalizes the just build it mentality we heard about in the beginning. It views managing human progress as a societal defect that needs to be overcome by technological force.
And that mentality is now clashing directly with the established forces of caution. Critics see EK as being divorced from social and ethical theory. They warn that technology, if it's unloosed without addressing systemic issues or replacing capitalist structures, inevitably risks creating a cyberpunk dystopia.
A hyper-efficient, technologically advanced world marked by massive inequality and a lack of human dignity for those outside the privileged loop.
Exactly. And that philosophical clash perfectly explains the regulatory friction we see across all three of these domains. The progress we've detailed, the PPW optimization, the Starship cost differential, the BCI and age reversal safety hurdles, it's all fundamentally challenging institutional control.
And this creates a textbook ethical confrontation between two primary schools of thought that inform policymaking. On one side, you have utilitarianism.
Right. This perspective is focused purely on maximizing the overall outcome, the greatest good for the greatest number.
So in the context of BCIs, or age reversal, a utilitarian argument would say the benefits curing widespread paralysis, extending productive lifespan, maximizing species-wide wealth via AI outweigh the potential harms or risks to a few individuals' autonomy. The beneficial outcome justifies the technological means.
Exactly. The focus is on the aggregated benefit. But directly opposing this powerful force are deontology and virtue ethics. These frameworks insist on respecting individual human dignity, autonomy, and mental integrity as moral duties, regardless of the beneficial outcome.
They prioritize principles like non-maleficence.
Yes, the obligation to avoid causing harm, even if avoiding that harm means slowing progress.
So the deontological approach would prioritize the neuro rights we discussed, that absolute right to mental privacy, over the potential benefits of widely available but ethically risky enhancement technology.
That's the core tension. And this clash is most vivid in the public opinion surrounding these enhancement technologies. You can see this anxiety reflected immediately in the data.
The survey results confirm this friction, don't they? There's widespread public concern about using BCIs for non-medical enhancement. Many people view it as morally unacceptable or as interfering with the natural order, even if they accept using BCIs for treating something like paralysis.
Right. And this public concern is not just philosophical. It directly fuels the calls for stricter regulation and protective frameworks like neurorights. It forces policymakers to prioritize that principle of non-maleficence, avoiding harm and protecting dignity, even if it means deliberately throttling the engine of progress slightly to ensure ethical oversight.
So you have the generative power of the builders, often backed by an accelerationist mindset, constantly pushing the boundary of what is possible in compute, in space, and in biology. And simultaneously, you have the protective force of the regulators, driven by these deontological concerns for human dignity, rushing to establish guardrails.
And that is the imperative for balance. The simultaneous acceleration in compute, space, and human enhancement represents an unprecedented moment of transformation. The challenge is not to stop this force of progress, which, history suggests is probably futile, but to manage it.
It requires ensuring that the principles of beneficence, doing good, and non-maleficence, avoiding harm, are meticulously balanced. It's about safeguarding human dignity and autonomy as we step into a future that will be fundamentally designed and accelerated by these converging technologies.
We must engage in informed decision-making, conversant with the engineering realities on one hand and these profound ethical theories on the other, to shape this future in a manner that respects those core human values.
This has been a true deep dive into the accelerating forces that are shaping the next decade. The infrastructure for intelligence, the platform for industrialization, and the tools for biological enhancement are all converging right now.
And the stakes of this generational choice to manage decline or to ignite the engine are playing out right now in the physical construction of desert AI factories, in the launch cadence of orbital rockets, and in the ethical protocols governing the human mind. The conversation ends here.